Hi everyone, my name is Namyoung of Samsung Electronics. I've been working for 10 years as a verification engineer for SoC design. Today, I'm going to talk about the way to maximize reusability of UVM test scenarios in SoC verification. I will talk about the verification challenges in complex SoC development using listen to SoC trend materials in motivation. And then I will present a novel approach to overcome the challenges by maximizing code reusability through hierarchical structure and by increasing test efficiency of scenario development. I will show experimental results for the approaches and close this presentation with a conclusion. I'd like to talk about lesson to SoC trend and challenges. As you all know, and shown in the left chart, SoC design is still getting increased, and the big size SoC is more required in the market. The large and complex design give huge challenges to timely development. So about 68% of SoC products were behind schedule as shown in the right side. From the perspective of verification, larger design requires more resource and time, as on-time verification is the key of the successful SoC. Here I bring two charts for functional verification. The pie chart in the left tells us where we spend much time in verification activities. Among the verification work, we focus on the third graded activities and try to find a way how we can reduce the time of creating TB and run the test based on the UVM methodology. As because the UVM is the most dominant tool in verification engineers, as shown in the right bar graph. We suggest two approaches to shorten the test scenario development period. First is to reuse the existing test code. Second is to increase the efficiency of the scenario. I will go into the details in the rest of session for two approaches in order. Proposed approaches are mainly targeted the system Verilog and UVM-based test because they are most commonly used language and methodology as already mentioned. Let me talk about the first suggestion, maximization of code reusability through hierarchical structure. Before go any further, I'd like to talk about reusable test code. Typically, SoC test code includes IP functional operation part and system level event or control part. So, the reusable portion can be defined for each part. For the IP functional operation code, we can reuse it when the same IP is used in other SoC products. As you can see here, even application is different, same version of IP can be used. And we can reuse the IP operation code over the different product. For system level test code, because each SoCs have their own system function, it is not possible to reuse the same test code. However, when category of system function is defined, we can also reuse the system level test code. As explained, we defined reusable portion in the test code and set up the strategy respectively. For the IP operation code, we suggest hierarchical code structure according to reusable definition. Based on the code role and purpose, we layered the UVM test code by using UVM inheritance. We can define and implement a certain test class without any dependencies. Then, we can have a fully reusable code I will explain on example later slides. For the system code, we suggest system API for the system-level events and control code. Since each product has own components and system events, it is not possible to create fully reusable test code for the system events. However, we can define typical system-level features such as system reset, interrupt control, and something like that. We encapsulate the test code itself for those features and implement the reusable API code. If we write a system scenario using the predefined API code, we can fully reuse the system-level test scenario because hardware-dependent code is hidden. I will also show you how we can enable this using an example code later. Regarding hierarchical code structure for IP function operation, we define 3 layers. The first layer has one class. The class contains all IP operation code using a handle rather than an instance of the verification components. The second layer has as many classes as the number of IP functions. This class inherits the first layer class, and it implements only the code that calls a specific IP function from the first layer. The third layer has as many classes as the number of IP functions and the number of IP instances of a product. This class inherits the second class, and it implements a code that connects each handle of the first layer to the actual instance of each product and test bench dependent implementation. Through this hierarchical code structure, we can minimize code change for each target product because we have product-dependent code only in the third layer. Thus, the first and second layer code could be reused without any modification. Let me show you a case applying the hierarchical code structure. This is the example of the first layer class. I use an UART IP for the reference and assume that there are 2 basic functions and 4 instances. As I explained, there is one class in the first layer. You can see some handles in declaration part. Those handles are used when implementing UART operation code. And you can also see 2 tasks to operate, transmit, and receive functions. In here, there is no body task. There is no creation or connection of the handles. Here is example of the second level class. First, second level class inherits the first level class, and then we defined 2 classes to perform transmit and receive function of UART. Second level class had the body task that was not in the first class. And the body task is implemented by calling the task from the first layer class. Here is the third level class, the last layer of proposed structure. There are 8 classes, and they have 2 functions for 4 instances are configured using macro method. Since we have to do the same work for many third layer classes, we use macro to solve code duplications. You can see that the actual instance of the interface, register model, class, and VIP sequencer is connected to each handle. Therefore, code changes by product or test bench configuration are occurred only in this layer classes. From this page, I will talk about the system-level test code reusability. When developing SoC-level test scenario, the conventional way is to mix up IP functional operation and system control code directly in a test scenario. However, it cannot reuse all the code because the system control code has product dependency. We came up with this scenario structure using three keywords: separation, modularization, and encapsulation. When developing a test scenario using this structure, we can reuse the system API code in terms of the usage form of the system control function. Let's take a closer look at our application cases. We completely separate IP operation code and the system control code. Then, we modularize the system control code for each system function. After modularization and encapsulation for the system control code, it is possible to introduce APIs. So, scenario developer can write a scenario regardless of difference between products by using this API. If the internal code of the system control operation is changed, we do not need to modify test scenario. The effect of the operation change is reflected in all test scenarios. Here, I give an example system API. As explained, the system API targets system function for general purpose. Reset, power, and clock features are candidates. I simply list up the APIs that we designed and used in this table. I think a user can extend the APIs by referring this table. I would like to introduce a way to increase the efficiency of complex and composite scenario development. After the reusable are ready, such as the hierarchical structure code and system API code, we can make library of them. We thought about how to make test scenario easily by picking the sequence or tasks from libraries and combining them. Usually, SoC verification engineer begins verification using the unit test and then add IP, sequence, or system tasks. Test scenario is extended from simple scenario to complex scenario, and attending IP sequences or system tasks are increased. Finally, a complex scenario can be created as shown in the right of a figure. This scenario contains all other scenarios on the left. If only the scenario on the right is verified, we do not need to perform the other scenarios, because the right one includes all other scenarios and has the same coverage comparing the others. It is the most efficient scenario, and it can be reduced the number of test scenarios. However, scenario development efficiency is low because it is made by the hands of the scenario developer. So we propose a metadata. The metadata has information about the sequence and system task order. On the left side of the figure, you can find the three sequence orders. Number one is serial order. It means sequence or tasks are performed sequentially. It can be expressed on a new line on the metadata. The bloom is that. Number two is for parallel order. When two tasks are operated at the same time, scenario developer use ampersand on metadata. Please find the orange. Last one is mixture of the serial and parallel order. Parentheses and semicolon are used for metadata. It is colored as red. Using these symbols, we can easily make a scenario in the text form. The metadata which is explained previous slide need to convert into UVM test code for simulation. We developed an interpreter for this. The interpreter is developed as Python and has 3 features. It parses the scenario from metadata, checks syntax, and generates the UVM code. This proposed flow using metadata and interpreter can increase the efficiency of scenario development because scenario development only needs to write metadata. I prepare an example of UART and API that were introduced earlier. I write the metadata as shown in the left side. UART 0, 1, 2, and hardware reset are performed at the same time. Then, serial software reset for block A and block B is operated with the UART 0 RX sequence. Finally, the UARTs are performed in serial order. I can make this scenario using only 5 lines of metadata. It is automatically generated to UVM code through the interpreter. We expect the benefits to use proposed flow. It can easy to implement complex scenarios without UVM background. We can also get fast freeing up without any error. It can hit the corner case with the efficient scenario configuration. Finally, we can achieve the target verification completeness in early phase and shorten SoC verification TAT. Let me show you experimental results. We used 2 automotive SoC products which have been designed on the same architecture platform. We verified the first generation product using legacy method. Then, we reorganized the test scenario written for the first product based on the proposed 3-level code structure. When we verified the second generation product, we developed the test scenarios by totally reusing first and second level code. We modified only third level code based on the second product configuration. This graph shows the portion of first, second, and third level code in terms of the number of code lines. Of course, the portions are a little bit different for each verification entity. However, you can see about 86% of total code line are reused parts on average. We choose the number of the test scenarios to fully verify the target entity as next metric for efficiency. If we can combine a set of simple test scenarios and make one equivalently complex scenario, efficiency can be increased. This is because the same coverage can be reached with a single complex scenario instead of a set of simple scenarios. By using the proposed metadata, we can easily implement very complex and composite scenarios which have very high coverage. This graph shows the number of test scenarios to complete target entities. Compared to legacy method used for first generation product, we can reach the same level of coverage only with 13% of the number of tests in second generation product verification. As a result, about 87% of total number of test cases can be reduced. Finally, we tried to classify or test code whether they are reused from the library, manually coded, or automatically generated by the proposed interpreter. The results show that total 44% is completely reused and 44% is automatically generated. This means that we can complete the full test code development only with 12% of hand coding. This implies that we can dramatically increase the efficiency and sensitivity of verification. Now, I'm going to show you the conclusion. In this presentation, I propose layering UVM code structure and automatically test scenario generation framework based on metadata and interpreter. Our results proved that many test scenarios can be secured at the very early stage of SoC design by using reusability. In addition, many complex test scenarios can be easily implemented by defining them in the form of metadata and automatically generating UVM code. The proposed methodology increased the efficiency of test scenario generation, resulting in TAT reduction of whole product verification periods.